All right. Today we're talking about internationalization for web developers. It's really for the web. There are parts that apply to more than just developers, but we are going to get like really nerdy in at least a couple of columns. So don't fall asleep during that part if you're not a developer or if you're a developer. This was a. For those from Family Search, I'm Jared. I work here at ICS on the Stack team. Disclaimer. I am learning this stuff just like everyone else. In the fall, our localization team wanted a developer from our team to go to the Unicode conference, and that ended up being me. It was a 3-day conference. It was about Unicode, and I thought, how in the world are we going to talk about this for 3 days? And it was actually very eye-opening. There's a lot of things to know here. It may or may not be interesting to you, but there's some very foundational parts that really apply. Will help you kind of understand how things work. So if you feel like you are an internationalization expert, or I say something wrong, please chime in. I would not be offended. I would prefer it. Or your feedback is definitely welcome. All right, so let's get started. So I heard some people talking about this before that, right? I18N and L10N, what the heck, right? So this is the code that you're going to see. You see it with accessibility, A11N, ALI. You see it with localization, globalization, internationalization. It just means start your word with I. This is too long of a word that I don't want to spell out over and over again, so I'm just going to count the characters between I and N. Okay? We didn't make this up. This is legitimate standard, okay? Well, let's see. Let's go full screen here. All right. So internationalization and localization, just kind of some root level terms we're going to discuss. Both of them deal with adapting computer software to different languages, regions, technical requirements of targeting a specific locale. But they mean different things. So you can kind of think of internationalization as a pre-planning stage. It's what enables you to take your product to multiple locales, all right? And then localization is actually the effort you put into taking your product to a specific locale. Does that make sense? So you're adapting what you've created to different regions or locales or markets. Questions, comments there?
Comments. It tends to be a little bit more of a focus on the cultural and unique local requirements than just the language.
Correct. Yes. Translation is one small aspect of this for sure. So to allow for localization, we write software that's adaptable, flexible, and enabling, so they, whoever they are, not us engineers usually, can take it and adapt it to a target locale, right? A specific adoption. So your internationalization efforts will have multiple localization efforts, one for each locale. That make sense? That you target. So for example, if in our internationalization efforts, things that we would do would be allowing Unicode, we separate content from source code, we don't hard code strings, we are careful how we concatenate or we just don't. We allow currency preferences to be customized, date, time. There's a long list we'll talk, but that's the gist. What that does is it allows, in this particular case, we're talking about Japanese, displaying and storing kanji characters, translating content. We can have a Japanese strings bundle. We have, we're not showing them things in US dollars, that type of thing, right? Does that make sense? Questions, comments? And like Gordon mentioned earlier, it's bigger than just translating content, right? We're talking about translation, but there's actually text in UI direction, number formats, number systems, time, date, time, calendar, currency, different types of keyboards and input systems, sorting. I mean, all these things, when you're going to a specific locale, these are things you need to be considered. It's a bigger problem than let's just take English words and make them a different language. Does that make sense? Questions, comments?
There's no particular order here. But the last column really stands out for what I call culturalization. Those items are very, very important, and you usually need in your UI design, you need to have lots of local people participating.
Agreed. Yep. The better you do this, like the more thorough you are with these efforts, the more natural that content is going to feel. So I think it's very easy to detect when there's kind of been a hack job between US English and maybe some other locale where we just maybe ran it through Google Translate and did some stuff. You could probably, people are going to sniff that out pretty easily, and it actually probably negatively affects our credibility. So, questions, comments about that? Does that make sense? All right. Kind of the foundation of all this is text writing, writing systems in Unicode. So who's familiar with Unicode? Like who's really, really, really familiar with it? All right.
I know what it is.
Yeah. So before us, that was me going into that conference. I knew what it was. Then I just like, oh, I didn't know what it was. Like it's huge. So kind of at a higher level, let's talk about written communication, right? When we write something in English into some sort of writing format like a book, there's already agreed upon meaning on characters. When you combine them, we put them in there. That agreed upon meaning allows us later to extract that back out from the book and understand what's going on, right? So in kind of the computer systems, it's kind of similar. This is maybe a simplification. But we type in or say hello to Siri in our iPad, and it kind of converts HELLO to these are Unicode code points for HELLO. That is stored in memory on your hard drive, kind of transmitted, maybe encoded, probably encoded. And then later on, either us, future us, or someone else far away can take that binary meaning of those text words, and their iPad tells them that it said hello, and we understand what's going on. Right? Does that make sense? That's a writing system. And so this is where Unicode, the Unicode Standard, comes in. So Unicode, what it does is it provides a unique number for every character, and we'll talk about what exactly that means, no matter what the platform, the program, the language. So this is kind of a lower level thing that is beneath. It's bigger than web development. It's bigger than Java. It's bigger. This is super low level. It's a standard. But the gist is every character has a number that represents it. And so it's a standard for text. That unique number is called a code point. So when I say the word code point, that's what I mean. It's actually referring to the number assigned to that particular character, right? And before Unicode, there were 240 other standards with regard to this. So Unicode replaces that. And according to people, this covers all known business languages today and then some. So things that are no longer around or no longer used. But basically, Unicode handles writing systems for pretty much everything. So kind of a really, really, really low level, kind of the very foundation. We talk about the Unicode Standard. Every character basically has some information attached to it. That's the code point, that's the number, the name, kind of the category. Those categories include whether like a letter, a mark, a symbol, a separator. There's some punctuation attributes and bi-di properties, which means bidirectional. And then for instance, like our poop emoji, that's code point. Here's the code on that. You can actually look at this big ginormous file and see exactly at the very lowest level what attributes are assigned to each particular character. Okay. So fun fact. So when ASCII, like the original, I don't know, maybe the original, there was room for only 128 code points, and in Unicode there are room for 1,114,112. So there's a lot more room to grow, and that number below 2 to the 16 times 17, we'll talk a little bit more why it's formatted that way in a second. Also a fun fact, there's a new release of Unicode every year, I believe. And Unicode 10 released last June added 8,500 or so more characters for a total of 136,000 characters. So out of that 1.1 million, right, we're using 136,690. Okay, and that includes 4 new scripts, so 4 new writing systems for a total of 139 writing systems. right? Is everyone, so a writing system for us would be like a Latin type of thing that supports English and Spanish, a number of things. So this isn't languages. This is kind of a level below that, where a particular writing system may have multiple languages on top of that. Does that make sense? So there's a difference between writing system and language, okay? And then, well, we got 56 new emojis, okay?
We didn't have
There weren't enough. I couldn't really properly express myself, so. Okay, this is really getting down in the weeds, but there are a couple of points here that you probably should take away from this. So all those characters are divided into what they call 17 planes. And plane 0 is called the BMP, or basic multilingual plane. And that's where most of our common Latin characters and really all common characters are kind of put in there. Not all of them, but the bulk of them are put in there. And those are your smaller code points, right? But then there are 16 other planes, and those are called the astral plane, which is going to be important in a minute. And they can contain a lot of the emoji symbols, some less commonly used characters, and they are the higher code points, which basically means that in order to represent them, it requires more space, more memory, more hard drive space, more everything, okay? And so these two things are plane 0, the BMP plane. These are kind of called the astral planes. Basically, this kind of the less common, but still you can't ignore it, or else you're going to die, according to that emoji. Yep.
So in your basic multilingual plane, do you have Latin alphabet, Cyrillic alphabet, simplified kanji, things like that?
So a lot of, yes, and kind of the less common, like CJK characters and things like that, and maybe ones that aren't used anymore would be kind of placed in the other planes. So there was a heat map that kind of showed out of all the 17 planes, vast majority plane 0, with some heat on that first one where you have it's probably emojis, honestly. So does that make sense? Questions, comments? Super geeky, right? It's gonna get worse, promise. All right.
We're wondering back here which one the Reformed Egyptian is.
I don't know. Sorry, you can look up the code point, and that would tell you based on the number. Yeah.
They do actually have the Deseret script.
There you go. I know that they have ancient Mongolian script because we haven't had that.
Really? Sounds fun. All right, we've been using the word character, right? And it may not mean what you think it means, okay? So it's a single logical unit of text. It includes things like A, B, C, 1, 2, some of your emojis, but it's not just that. Sometimes it's actually like these things too. That could be a separate character. That make sense? And that thing below, I'm mapping over each of the things in that in a way that I'll get to later. But essentially, those are the code points for each of those characters. That make sense? Questions, comments? Who's bored? Raise your hand.
Miss Jenkins in kindergarten told me that there's 26 letters in the alphabet.
That's true.
I'm sticking with that.
Okay. All right, we talked about characters.
Miss Jenkins is dead.
There's graphene. Moving on. There are characters, graphene, splits, ligatures, ideograms, logograms. This is kind of that bigger world I was exposed to that I was talking about. All these things are meaningful, okay? We'll kind of talk about that a little bit. But before we do, I got a pop quiz. All right, here we have our family emoji, and we're removing the void, and we're replacing it with an empty string. Raise your hand if you think the answer to that is A. Don't be scared, okay? Raise your hand if you think it's B. Raise your hand if you think it's C. And then D. All right, what should we see? All right, sorry. So the answer is what? Now, who can explain that?
There's some intelligence going on.
Anyone?
They gave away tickets. You took away the boy, so he's obviously God.
Yeah. All right, these are kind of these new terms we're talking about. Right? So ligature. So there are kind of things naturally that happen. For instance, I think our ampersand is actually the evolution of what is the Latin of ET being used over and over together. They finally just combined them, right? So that's kind of the gist. That ligatures, when two sequential graphemes are represented by one glyph. And we'll talk about graphemes and glyphs. So a grapheme you can think about as the smallest unit of writing in any given language. It's kind of the user-perceived character. Yep.
Are these slides going to be made available?
Yes. Yeah. $10.99. Just kidding.
You can go sell your teacher.
So a grapheme is a user-perceived character. Okay, that's how we think of things. And it could be a single code point or it could be multiple. So we can actually construct potentially a single grapheme with multiple characters. Okay, and that's like letters, numbers, punctuations. The entire like Chinese, Japanese, Korean character would be considered a grapheme. And then there's the idea of a glyph, and that's the single visual unit of text. For instance, these are all different graphemes, right? With different glyphs or different font styles, right? And also, there is a one-to-one connection between the character A and the grapheme, but not the glyph, okay? And kind of the back to that trick is you can represent a sequence of characters with a single glyph if you want to. Does that make sense? So in our little playground here, we can add family members, remove them. And I don't know if you can see the code or not. Essentially, I have each of those individual emojis separate. And depending on which ones you select, I am joining them together with a separation of this invisible joining character, which is a Unicode character that you can't see, but it's there, right? And I mean, there's definitely some copy and pasting that happened there, right? And then depending on that, whenever my particular font set here sees, man plus joining character plus woman plus joining character plus girl plus joining character plus boy, it's like, hey, when those things come together, I'm going to represent it with that glyph. Okay? So that's how that replacement worked.
So are you using the joining character to create a 4-part ligature, which then maps through Unicode to that glyph, which is the 4-people family? Is that what's happening?
So if I copy this, maybe this will answer your question.
Just to try and understand the relationship better between ligatures and graphemes.
I copied that and pasted it there. Okay.
So what's that mean? That doesn't help.
Can you make that?
I mean, we were talking literature.
So what happened?
What standard committee decided this?
Unicode. Yeah.
Ms. Jenkins did not mention
No,
that.
she didn't.
So what happens if you replace a girl with another boy?
It depends on your font. So really, this is a combination of things working together. If my font system, my font family, or whatever font I have that's handling Unicode, it determines whether or not it's going to show that as however it wants to show it, right? But under the hood, this is what's happening. Man, joining character, woman, joining character, girl, joining character, boy. Okay?
Well, do 2 girls and 2 moms.
So that depending on your font, because we're in the world we're at, that would actually work. So.
Okay. So it,
So if you want me to, hang on one second. Oh, I should probably say it's a string. There you go. So just so happens that my font family recognizes that. There was a question.
It's very PC.
so
Well, this isn't just for emojis. This is to things like kanji, which are made up of individual bits.
Get to that, but kind of, yes, sort of.
So if I'm a font creator, I have to create these if I want them to be represented as a single glyph. That I see this combination, that means I'm going to put this character rather than these individual characters.
Does anyone here create fonts? Not here. So my understanding of that's true.
So what font are you using?
This is built in, whatever came with a Mac.
Do they have to handle all permutations or just all combinations?
So I think my understanding is that it just works on sequences. When they see these sequences, they have to account for it.
So if you did girl, girl, boy, boy, or, 2 kids, 2 parents, it would not work.
So I don't know, but let's say you're a Mormon and you wanted to create a font that represented a Mormon family.
Yeah,
You
like
could
my
say
ancestors.
2 kids, or 2 adults, 7 kids, and then have an emoji that would be up to you.
What about my great grandpa with his 30 wives?
Whatever it takes.
So I missed the answer to, is that a ligature?
Yeah, like, so I really want to know.
So in the font, that's considered, yes, that's a ligature.
Is there anything else as well?
I don't know what you mean.
Go back to there are other things like, for example, like the U.S. flag where it has the U.S. character on it.
Yeah, I heard of this.
There's a lot of the Asian scripts have this.
Yeah, so that they can be, ligatures can be done at a font level, but there are legitimate Unicode characters that show a ligature.
So what is a grapheme then? I guess I just want to understand. I know what the glyph part is. That's understandable.
This is basically has nothing to do with technology. It has to do with humans, how we see things. So when we see this pattern, the shape right here, no matter where it's written, right, that's a grapheme. We recognize that shape to mean something.
Oh, okay.
So when you constructed the family emoji, you have that joining character between each of the other characters?
Yep.
Is that true of the other sample ligatures that you have there, like the AE? Would you need a joining character to say these 2 things should become?
I imagine there already is a single Unicode character representing that ligature. So there's 2 ways you can create that. There can actually, you can put into a character that, or in a font you can plan for, like I don't know if you've ever seen particular fonts for developers, like, pound or exclamation equal JavaScript, right? Some fonts will convert that sequence of things to actually look like equal slash through, equal, like the math symbol for not equal. So you can do things like that.
I do know that, like with Relation, right, it's not actually the font that determines how it's drawn.
Yeah. So there are a number of ways, but the concept, yes, that's true. And we'll talk about some of those too. But just the kind of idea, like kind of understanding, like these are distinct different things that have really good meaning, especially when you talk about internationalization and how you accomplish some of these things. Any questions or comments?
I think the main concept here is that you need to make sure that your input font matches your CSS so that it can render the font as the code points represented.
So if you're relying on the font to put those together, you better make sure you're using the right font. Right? Is that what you're saying? Okay.
How would you generate the AE using your console?
How would I do that? There is probably a unique Unicode character for it. So if I wanted to find it, I could try.
Oh, you just can't combine the 2 ligatures?
So here you go. There is an actual Unicode character, 1 code point that produces this ligature.
So if you know the code point, for example, like if you hit Alt 164, you'll get an NA, for example.
I trust you, yeah.
Right, and I just learned to do that when I write an email with my Western keyboard that doesn't have NA. So that only works on Windows. It only works on Windows.
Yeah.
On a Mac,
You can do it all you want on another one.
How do you just bring up that little?
Control Command Space anywhere will bring up that window where you can select emojis or other things. Question?
Tell me if I understand this right. If the ligature is implemented on the font level, then the font decides whenever I see an A and an E together, I'm just going to render this glyph. But Unicode wanted you to be able to put 4 people independently, or sometimes also make family. So they have the join character, and if you join a bunch of characters with the join character, it's going to try and find a ligature for it. If not, it'll just render the form.
So I think so, except for I don't think they added that joining character just to make emojis that become ligatures. Like it has other purposes.
Oh, we're not there yet.
Okay. Another question. Good. It's good. Good thing we reserved 2 hours.
Pizza's gonna be cold.
Okay, moving on. Maybe. All right. This column of slides, this is the one I'm more than you about. This gets really, we're going to actually talk about binaries a little bit, okay? So, really geeky. Feel free to snooze for the next 5 minutes or so if you want to. All right. Pop quiz, another one. Another 2. So, who's familiar with the syntax? It's basically the equivalent of dot index of, or dot, char at, or kind of that, right? The idea that, hey, the character at position 2 in this string is it you? Is it 1? Is it you? Is it 2? Is it you? Right? So who thinks it's A? Raise your hand. B. C. And D. All right. How about this one? Same idea. Here we have bacon equals love, right? So I'm saying, tell me the position of that equal sign. Is it character 0, 1, 2, or 3? Raise your hand being A. B. C. D. All right, should we see? Hey, this is how I felt all during that conference. So that one, false, true, which I think was C.
Yes.
Right?
It takes 2 characters to make 2. Because there's the poop and then there's the I. I don't know if that's
And 2 is the answer to that one. So C.
No, I didn't get that. So it's not.
That's logical, right?
It's clearly 2 pieces of bacon.
So a joining character doesn't count as a character.
There were no joining characters there, but it would. It was a character.
But that requires a UTF-16.
Yeah. So, all right. Yeah, sort of.
Is it always 2 bytes?
No.
Oh, that's why I thought that was such a horrible question.
No. All right. Well, let's look at why, or just snooze for a little bit. Either way, right? So we, as a person, we type in a bacon or a 2 pieces of bacon, whatever how you want to look at it. We put it in our iPad. We want to store that in memory on our hard drive. We want to send it across the wire, whatever the case may be, right? So the code point for A is in decimal is 65, like that's how we think, right? And for bacon, it's 129,363. Okay? And the very biggest number we can have in Unicode would be that, and that was what it would look like in binary. Okay? So that's the binary representation. Now, if you're storing this somewhere, right, this is a lot of wasted space to say 65, right? Like doing that, we could do that in decimal too, 0.0000000000065, right? And we could do that, but that's a lot of extra space. That's a lot of extra things to send down the wire, to even put in memory. Like it's just not, we don't do that. It's inefficient. And so what we do is we encode them, right? We add code to our code because that's what we do, right? So Unicode encoding, it's an algorithmic mapping from every Unicode code point, that number, to a unique physical bit sequence called a code unit. So there's some abstraction there that happens, right? And these are kind of your most, these are standardized ones. There were a whole bunch of others at some point, and these evolved from other things. But essentially, you have UTF-8, UTF-16, UTF-32. We've probably all heard of these terms and have some level of understanding of them. Okay. So each of those are different algorithms to represent that big, long, inefficient number to by another number. That's basically what we're doing. And for instance, in UTF-8, which is the recommended one for web documents, it can be represented in anything from 1 to 4 bytes, which makes it good that we don't have to send down 4 bytes for every single thing. It's a variable width. And here's kind of the algorithm, how it does that. If your byte 0 starts with 0, we're saying, hey, this is only, right, a single byte character. This is basically your first 127 your ASCII characters. So it's UTF-8 is backwards compatible with ASCII, or I don't know if I said that right, but you get the gist. All right, and then so on and so forth. That if the code point, right, is large enough, at some point in time we're going to have to use in UTF-8 we're going to have to use 4 bytes. Okay. So the gist here is that it's not good enough just to send raw code points down the wire because it's inefficient, that there's different ways of taking those code points and making it more efficient to store, to save, to send, all that kind of stuff. Right? Okay. So back to this problem. In JavaScript, the way that strings are represented is with a Frank encoding. Okay? So JavaScript uses a 2-byte fixed width encoding to store each character. And it kind of roughly translates to this mixture between UTF-16 and this thing that came before that, which was a fixed width thing called UC2. You don't really need to know the names. But the gist is UTF-16 is variable width. So UTF-8 was 1 to 4. UTF-16 is either 2 or 4, right? You never get 3 or 1. It's either those two. And it works by, if it's a large enough number, there's some encoding information in that first one to tell whoever is receiving it that there is another pair, a surrogate pair coming with it, and to process both of these things together. Okay, that's the gist. Well, in JavaScript, it works sort of like that, but also works sort of like UC2. This is at a string level. There's other parts that are actually UTF-16. But this is why we're having this issue, is that it kind of, in parts of JavaScript, it defers to the rendering, kind of that reorganizing of surrogate pairs, right? So if you have 2 pairs of bytes that belong together, because you were talking about a really long a character with a very high code point, like this hamburger menu plus an extra layer.
It's a big match.
Big match. Right? That if you actually take the length of that, you're going to see that JavaScript thinks it's 2, because it requires 2 pairs, both pairs of a surrogate pair. It requires 4 bytes to represent that character. And that's why that's happening. Okay? So if we were to look at that, we can kind of see that's true. What happens when we actually take one and concatenate it with the other? Hey, look, we have both parts together. Okay? That make sense? No?
Yeah.
All right. Like I said, snooze if you want. If it helps, it helps. So, how do you solve this problem, right? Because really we're just trying to ship things. It's good to understand why, because it'll help you diagnose and understand and maybe solve problems faster. But at the end of the day, it's about solving the problems that we come across, right? So, JavaScript went through like a 10-year dark ages period where nothing happened, and a lot in technology changed during that time. So before ES6, like there was not Unicode stuff, right? And so newer APIs are being added to JavaScript that are much more friendlier towards Unicode. For instance, the iterator, there's a string iterator that's been added that's ES6 aware. So all of these things here, essentially under the hood, invoke that iterator, and that iterator speaks Unicode. Okay. So kind of some good advice in general when you're thinking about strings. Don't think about them as a sequence of glyphs. That's not what they are, right? They're a sequence of code units. That's what you're getting. Right? Does that make sense? All right, let's leave this geeky area for a little bit. Okay. Questions, comments about that? All right, string normalization. Pop quiz. Without running this code, is this true or false? Raise your hand if you think it's true. False. Raise your hand if you think it's false. Raise your hand if you think literally nobody knows without running this code. Yeah, literally nobody knows without running this code. You have to run the. You would have to know the answer to this. You would have to run this code. It could be 1, or it could be 2, or it could be more. You don't know, honestly.
What is it?
Well, the problem, I show you this, that's one possibility. Like, this is just how I implemented it. So in this case, this is, I believe, false, but it could be true. It just really depends on what I actually did here. Okay? Clear? Clear. All right. Furthermore, I have string 1 and I have string 2, and they look the same to us, right? We look at those, and they look the same. And then we run them through our computers, and we're like, hey, computer, are they the same? And what do you think? Well, we don't know, right? Can the computer know? Like obviously, like to us, these mean the same thing, right? But they don't mean, like to computers, they don't mean the same thing. All right. You guys are scared to answer now. It's kind of funny. All right. So fun fact. In addition to characters, in Unicode, there is something called combining characters, and their job is literally to attach to other characters, right? That's what they do. And so you could do, like this right here, this isn't an image, this is text. I just wrote the word the matrix and attached a bunch of these. Well, I didn't, the internet did, and I just copied and pasted. Right, and they just attached a bunch of these combining characters to the words the matrix, right? And if I were to take this character plus this character, and I copy and paste them individually, really at a really, really low level under the hood, outside of the control of really anything, right? I could do oh, I didn't copy the right thing. I think I'm getting 2. This is the problem working with Unicode.
How many are you talking about?
Sometimes you just have to Google combining. Problem is my thing, no, it's not. It attached to the space, and I can't unattach it right now. That's what's happening. That makes sense?
Because it keeps copying in space and then
There's a space underneath it.
There's a space before that, and it's like, oh, I combine things. That's what's and I can't get to it.
And that's your operating system saying, hey, this obviously is supposed to be attached to this space.
Maybe I can get it here. Let's see if they did. Hey, there we go. So J, A, R, right? I can attach it literally to anything, right? That makes sense? And like this is just a text editor. You do this in your URL. This is really like low-level Unicode. No matter where you do this, this is just the behavior.
What happens if you paste it again after the R?
In that case, it doesn't know. But some of them, yeah, yeah. So if I were to look at this right here, for instance, and I were to copy that and like do a Does that make sense? So in Unicode, there are a set of characters. Like we're kind of fooling around with this because in our Latin perspective, we don't really care, or our English perspective, we don't really care so much about them. But in many, lots, most, I don't know, other languages, this is an important concept that you could actually construct a single grapheme using multiple of these characters. Yeah.
Important concept here. I have characters, now you add them together using one first and the other one second, or vice versa. What happens when you try to search for that string?
You need to have a Unicode-aware search algorithm. That. We'll get to that in a little bit, and that might answer. Okay. All right. So if we were to copy these things individually in a way that that tilde thing didn't attach to a space, we would see that first one work. And if we actually did it separately here, and even put it on the slide, right? I had to like attach this because it was attaching to the space. Like, it's just, this is really, really low level. That's the gist. But essentially, the reason why all that code before that was problematic is because you could construct that enya in many different ways. Okay. So, for instance, right, string comparison is not that simple anymore. Right? Once we're out of the ASCII world, it's no longer easy. So there's this angstrom character, which is this thing. There are 3 legitimate ways to create this character. There's not a right way. There are 3 right ways. They mean the same thing. This is true of every language, every programming language. Okay. So down here below, if we run that, that would be false, because I mixed these 3 things together.
But it could be true.
Well, I know it's false because of how I did it. You don't know.
That's what's fun about writing.
Yeah, you don't know. Like, you can look at it and you literally don't know whether that's true or not. Okay.
Well, I think having dealt with different Unicode schemes, so there's something called a byte order mark, right? That basically will inform whatever display you have how to render these byte orders.
I think that depends. Like, my understanding, that depends on the encoding.
Yeah, that's what that
Yeah.
drives that, right? So everything is really just a byte underneath. Everything's a byte array. Like everything underneath, fundamentally, the structure is just a byte array.
Yeah, we need to stop thinking about glyphs. They're not, right?
What's the representation we need to forget about? Because this is just representations for all those things.
Well, so when you say UTF-8, like when you do JSON, when you're like in headers, because we're dealing with like information systems. Generally speaking, there's something that will tell you exactly what encoding scheme is going to use. So then it just starts like left to right or right to left, depending on how it's configured. And it just starts reading 1 byte out of the array at a time. It says, I need to combine these 2, these 2, these 2, these 2, 3, 4, these 2. And so you have to stop thinking about the double quotes in the string and the like from the information down to the very bottom, it's just a big byte array that just starts taking 2
Correct.
or 4 or 3 or 1 bytes at a time and then displaying them in your IDE or on the web page or in the browser. Like, so if you think about that, but that's,
I totally agree with you. I think in the front end space, it's nice because usually this level is kind of abstracted from us. But as you can see, this is a very leaky abstraction, right? Like, we're seeing weird things happening, and to understand why it's happening will help you fix it. Okay.
So is the binary the same on the first versus the third? Or are they different binaries as well?
That first and third version of the angstrom.
Yeah, these are different. They're different code points for the same character. I don't know why. For the, I'm sorry, 2 different code points for the same grapheme, different characters.
What was the capital version?
Is that it? So let's figure out, like, that's great. How do we like deal with this? Okay. So in JavaScript, in ES6, they added they added a method on all strings called Normalize. Okay. And as you see here, this, if we were to run that, that's going to be false because we're just triple equaling them raw. Down here, we're normalizing it. It goes through this kind of low-level processing of, hey, Unicode also has this awareness of what things relate to each other and how to handle these situations where maybe they added these combining characters in different orders or whatever. So this would be false, this would be true, this would now be true because we're normalizing the string. And this is baked into, I mean, this is JavaScript, but it's from fundamentally a lower level of stuff that pretty much, if you spend most of your time in other languages, probably have equivalent things.
So is that recommended that we should just compare strings use normalize?
I mean, yes, especially if you're accepting user input, where you literally have no idea what's coming, right? Then yeah, right? But if you have an understanding of the entire, architecture coming through, like how you're storing it, what's there, like, so yes, to be safe, if you don't know what it is, yes.
So with the normalization, if you did that, if you just put in a regular end, would it match the one with the tilde?
Say it one more time.
If you just put in a regular end, would it match the end with the tilde, or do the
No.
characters have to be?
We'll talk about that right here. It's a good question. One more question.
Was the dot normal just a Boolean returning whether or not is?
No,
what was
it-
that?
It normalizes the characters to be the same. So like the AA thing that you showed earlier would actually be equal to true now, because if you did the normalize them both, right?
Yeah, both of these questions, wait till after this slide and see if he answers it.
Well, I think my question was different. It was, you had the double ampersand and then dot normal.
So here I'm taking each of the strings, I'm running each of those through that normalize, and then I'm comparing.
Oh, sorry. I was misreading down below the yes.
Okay.
Never mind, sorry.
How are we doing on pizza? Is it here?
It's here.
All right, let me finish this column and then kind of go from there. Really fast. Sorry to keep hungry people waiting. Okay, so that normalization process, just think there's 4 different ways of taking a string that could be any sequence and kind of standardizing it, right? And the 2 that honestly you should probably care about would be this one and that one. And they're just different algorithms that the end result is a canonical way of representing a string, right?
Which two were they again?
For web developer, I don't know your role. For web developers, this one and that one, okay? And the reason why this is used in JavaScript for your strings and things like that. Down here, when you register a domain name, like I'll talk about in a minute, but they want to do things like preventing you from, I'll show you in a second. The gist is, you have a string, it can be decomposed, reorganized, and then put back together in a way that they considered the standard way to arrange these characters. And so that's what we were doing with the NEA on both of those things. We were decomposing, recomposing it into the standard way. This one kind of just decomposes it and then sorts it in an appropriate way, okay? And the reason why that last one, right, let's say I have fluffy.com. There is a ligature character, actual character in Unicode. Like I could do some mean things to people, right? And make them think that they're visiting my site when they're actually, or visiting this thing where they collect credit card numbers, and I'm sending them to mine and getting their credit card number, right? So this is why that NFKC, normalization form compatible composed. Got it, right? It's just the way that it looks at it and wants to make sure that, yeah, in some cases, in some circumstances, the separate characters FF right next to each other mean the same thing as the ligature F. And that means that they are compatible. They maybe look different, but sometimes they mean the same thing. Kind of at a low level algorithm, there's some tools that help you determine that. All right. Okay. So let's see.
If you want to eat, we can get more present. Grab some pizza and then come back.
I have a time, yeah. It's up to you guys. I don't really care.
Why don't we just take a quick break and get some pizza, and then those who want to stick around and kind of see what else you've got.
All right.
We can do that.
All right.
Drinks are over on the left. Pizza's at both tables.
This is fascinating. The layer upon layer upon the building blocks that